Well, let's now look at some of the strong analytical capabilities in this module. Okay, so basic motion, or really more properly under the motion study, the full-blown motion study. So you can subdivide those between kinematics and dynamics. So kinematics would be just the study of motion itself. But now from the standpoint of knowing precise velocities, accelerations, things like this, and then dynamics, which we're not going to cover to any in any substantial extent in this video lecture, that would bring into the fold the forces that are generated or required in order to achieve those motions. So this universal joint gives us a very good platform for that. I mentioned, recall that this is only suitable when you have a relatively shallow angle of misalignment between the input and the output shaft, or when you're going slowly. If those conditions do not occur, as might be, for example, the case of a front-wheel drive vehicle, then what you need is a constant velocity joint, not a universal joint. The universal joint, in fact, does not transfer velocity uniformly from the input to the output, and the higher the angle, the worse it gets. Okay, and that's an effect that we can very readily see here in SolidWorks. So let's find out how we do this. So first of all, we'll turn off our interference detection, clean up a few things. In fact, we'll just go ahead and delete all the keyframes. In effect, basically start the motion study from scratch. Okay. In this case, I'm going to edit the motor to have a constant speed of 100 RPM. Okay. And we'll go ahead and create or recreate the motion as we had before. Okay. And now what I'm going to do is, under results and plots, okay, for this particular simulation, which has run at a constant input speed of 100 RPM, we're going to plot the input speed and the output speed of the lower yoke. Okay, and that will give us an exact representation, well, within the numerical accuracy of the simulation, of course, a representation nonetheless of the non-constant velocity nature of this mechanism. Okay, so I turn on the plots. Now it's alerting me that I need the motion analysis. Okay, so that's fine. We'll go ahead and enable that. Remember that in order to do this particular type of motion analysis, you would need the proper version of SolidWorks. Okay. So let's see. We'll go here to the plots, and here in the plots, we are free to select from all the components within the assembly and what it is that we want to plot. Okay, so in this case, we want to plot the velocity. Okay. We do want to plot an angular velocity. Okay. And we're going to want to plot the magnitude in this case, and we're going to plot the magnitude of the input. Okay, so we'll select this component and create a new plot. Now we should get something in the 100 RPM range. Okay, so again, notice there's some digital noise in there, as it were, but this is all centered around 600 degrees per second, which is of course 100 RPM. So if we double click on the axis, we will be able to affect the scale. So instead of having an auto assignment of the values, we can make the values go, say, for instance, from 0 to 800 degrees per second, and now we just get a fairly steady line in there. And of course, yes, we should do the major units at 100 and the minor units, say, at 50. Okay, so that gives us a cleaner graph. Okay, so that's our first plot. And now we can do similarly. We can set that plot aside and go back here to the plot results. Go through the same selection in here, angular velocity, but in this case the magnitude, and in this case we're going to select the output component. I'm not sure why that guy came off in there, so we'll let it be. And notice that we have in fact a sinusoidal output. Now the sinusoidal output, of course, better have a mean of 600 RPM. Naturally, you're not going to be able to go any faster or any slower on the average But notice, that we in fact are going to have this sinusoidal motion superimposed on the output shaft. Okay. Now we can, of course, go through the same exercising here and set up our scale to be from 0 to 800 with major units of 100 and then minor ticks here at 50. Okay, so now we can put both plots side by side and have an idea of this is comparing with the same scales, the difference between the input motion and the output motion. So I think very, very revealing. Okay, in fact, if we look at it in this manner, a very revealing behavior of a universal joint. Now, of course, you can combine these plots. You can export the data so that you can later analyze it in Excel or MATLAB. Anything that's of interest to you, you can apply forces. You can have the effects of gravity taken into account. You can report, the forces, reaction forces coming back from the various components. You can enforce coincidence or rather collision between components. You can enforce frictional conditions, and really a whole suite of utilities that would allow you to do extremely sophisticated rigid body mechanics analysis, which I think is wonderful both for specific engineering quandaries or problems that you may have with your prototype, but also very useful when it comes to understanding just the basic physics behind these effects. Okay, so I very much encourage you, as you learn, the physics that underpin all these effects, your classes in dynamics and in rigid body mechanics, etc. Whenever you see those exercises, and as you learn the theory, go back and put them in SolidWorks. Check it for yourself. Let SolidWorks illustrate for you the physics that's behind. Of course, it's doing it via a completely different approach. There's a lot of computation behind looking at the mass of the parts and discretizing the model and integrating and doing a whole bunch of differential equation heavy lifting there that you don't need to be aware of. But the results will be comparable and certainly useful and applicable to the theory that you learn.